Good evening, friends. Welcome to yet another lecture on chemical engineering, thermodynamics. I am Professor Arvind Prasad. Today we shall study about properties of non-ideal mixtures and the Gibbs Duhem equation. In today's presentation, you shall study about non-ideal mixtures and we shall follow it up with a problem for better understanding. And we will derive the Gibbs Duhem equation and apply it to a binary mixture. If we prepare a mixture as shown in the right by mixing non-ideal fluids or ideal fluids, and if M is a property of the mixture, then the change in property is equal to the change in property with respect to the temperature, that is the first term, change in property with respect to pressure, that is the second term, and in change in property with respect to addition of moles in the mixture at constant temperature, pressure, and holding the other species constant. Now, some clarification is required on this. This is change in property of the mixture for addition of a particular species holding the other species constant at constant pressure and constant temperature. Now let's understand it with respect to a binary mixture. Supposing I am adding M1 and M2 to form a mixture M, where M is the property of the mixture. This particular integral would be dou Nm by dou N1 into dN1 holding T, P, Nj, that is N2 constant. What does this mean is we stop adding 2 and only add a very small amount of 1, and the change in property of the mixture to a small amount of addition of 1 is dou Nm by dou N1 dN1 T, P, N2 constant. Similarly, if we stop adding 1 and only add a small amount of 2, the change in property of the mixture to a small addition of 2, that is dou Nm by dou 2 holding T, P and N1 constant, is this term. Therefore, if we have I species, we would have similar such equations for I species. And this is what is this entire term. Now, dou Nm by dou Ni, T, Nj constant dNi is the partial molar property of the mixture. Therefore, the partial molar property of a mixture of a species I in a mixture is the change in total property of the mixture to small addition of the species. Now, for non-ideal mixtures, the total property is nothing but the summation of the moles of the individual species multiplied by their partial molar properties. For a binary mixture, we can write that the total property is nothing but the mole fraction 1 of 1 into the partial molar property of 1 plus the mole fraction of 2 into the partial molar property of 2. It should be noted here that the partial molar property of any species I in a non-ideal solution is never equal to the property of the pure species. Therefore, we have that the property of the non-ideal mixture is equal to the summation of the moles of the species I multiplied by the partial molar species of I. It will never be equal to the moles of I multiplied by the pure species molar property. Therefore, for non-ideal fluids, we can write U, that is the total internal energy of the mixture, as equal to the summation of the mole fractions multiplied by the partial internal energy of the species I in the mixture. Similarly, the enthalpy is nothing but the summation of the mole fraction of the species I multiplied by the partial molar enthalpy of the species I in the mixture. The similar reasoning goes for entropy, Gibbs free energy, and volume. Now, we define something known as property change of mixing. The property change of mixing is nothing but the property of the real mixture minus the property of the mixture if it was treated ideal. Please remember, xi multiplied by the pure species property I, the summation of that will give you the ideal solution property or ideal mixture property. So the real mixture property minus the ideal mixture property is nothing but the property change of mixing. Now let's understand this further by taking an example. The volume of mixing for a non-ideal solution can be defined as the volume of the non-ideal solution minus the volume if the solution were treated as ideal. If the solution was treated as ideal, its volume would be nothing but the mole fraction of the species in it multiplied by its pure volume of the species. Let's understand it by taking an example. 100 ml of pure sulfuric acid is mixed with 125 ml of water at 20 degrees Celsius. Find the volume of the resulting solution and the volume of mixing. Now, 100 ml of pure sulfuric acid at 20 degrees Celsius will have a specific gravity of 1.8305. Therefore, 100 ml of pure sulfuric acid will weigh 183.05 grams and 125 ml of water will weigh 125 grams. The resulting mixture will be 308.05 grams. The concentration of the resulting solution is 59%. Therefore, the density of the resulting solution from the table will be 1.4987. And therefore, we can get its volume, which will be 205.55 ml. Now, what do we find here? If the solution were ideal, then 100 ml of pure sulfuric acid and 125 ml of pure water should have resulted in 225 ml of solution. But the resulting solution now is 205.55 ml. So the volume mixing is nothing but the difference of the real solution volume minus the ideal solution volume, which is nothing but 19.448 ml. Now, why does this really happen? Liquids and gases which are polar are non-ideal. Non-polar molecules behave like ideal solutions or ideal fluids or ideal gases. When we mix two polar molecules, what is going to happen? Or when we mix two polar solutions, what would really happen? Now, in any polar solution, the molecules are going to get attracted to each other because they are going to have a dipole. The molecules are nothing but a dipole. Now, when two such solutions, which are polar, are mixed, these dipole bonds are broken. The bonds between the molecules are broken. The bonds between the similar molecules are broken, and bonds between dissimilar molecules are formed. This results a change in volume. Well, if both the molecules were similar and the bonds were broken and reformed, there would be no change in volume. But now here, because the two molecules are dissimilar and the bonds are broken and reformed between dissimilar molecules, there is a change in volume. Therefore, whenever we mix two non-ideal liquids, we will have a volume of mixing. Now, the volume of mixing may be positive or it may be a negative quantity. This depends on how much are we mixing, the quantities that we are mixing, and the nature of the bonds. Let's take another problem now. Now, 328 ml of sulfuric acid at 20 degrees Celsius is mixed with 400 ml of water. The mixing is done isothermally and isobarically. What is the heat released? Now, 328 ml of sulfuric acid at 28 degrees Celsius is 600 grams. It is mixed with 400 ml of water, which is 400 grams. At the same temperature and pressure. Therefore, what do we get is the resulting solution is a 60% solution. The 60% solution has an enthalpy of minus 320. Now, if the solution were treated as an ideal solution, its enthalpy is 0.6 multiplied by 10, which is nothing but the enthalpy of pure sulfuric acid at 21 degrees Celsius, and 0.4 multiplied by 90, which is the enthalpy of pure water at 21 degrees Celsius. The enthalpy of mixing is minus 362 kilojoules per kg. Now, whenever we get a negative enthalpy of mixing, it means the mixing is exothermic. Heat will be released. And this is common knowledge that whenever we add water to sulfuric acid, heat is released. Now, the explanation here is the same as the explanation given for volume. The bonds between the sulfuric acid molecules are broken, and bonds between sulfuric acid and water molecules are reformed. The breaking and reforming of the bonds is common knowledge in chemistry. Energy is released. And therefore, we do find that energy is being released in this problem. Well, it may happen that energy may be taken. It may be an endothermic process. It all depends on what is the nature of the bonds and what is the system. Now let's put our attention to or turn our attention to Gibbs Duhem equation. Well, we all know if non-ideal fluid, for a non-ideal fluid, M, that is the property M, is nothing but the summation of the mole fractions and the partial molar properties. So we can write dm is equal to this. Now expanding it, we can write it this way. Now dm is equal to dou m by dou t plus dou t Now let's turn our attention to the Gibbs Duhem equation. For non-ideal fluids at constant temperature and pressure, now we know clearly that the total property is nothing but the summation of the mole fractions and the partial molar properties of the species. Now if we differentiate this equation, we get dnm is equal to summation of mi bar dxi plus xi into dm bar. Now we know that dm is equal to dou m by dou t dt plus dou m by dou p dp summation mi bar dxi. Now this equation actually comes from here. We take this equation and just divide it by n, that is the total number of moles, and we get this resulting equation. Now this equation, if we apply the condition of constant temperature and pressure, we get dm is equal to summation of I mi dxi. Hence, with this equation and the previous equation, note this equation, we add this equation to this equation and we get xi dmi bar dp is equal to 0. Now this is known as the Gibbs Duhem equation. This has a lot of application in solution thermodynamics. Let's see one such application. Now for a binary mixture, we have the total property is nothing but x1, that is the first component, multiplied by its partial molar property plus x2 into m2, where m2 is the partial molar property of species 2. Now dm, that is differentiating this equation, we get this x1 dm1 bar plus x2 dm2 bar plus m1 dx1 plus m2 dx2. Now from Gibbs Duhem equation, that is applying Gibbs Duhem equation to this, which is nothing but this, the Gibbs Duhem equation is this, we had already derived it out, and also applying the condition for a binary system that dx1 is equal to minus dx2, we get the following: dm by dx1 is equal to m1 bar minus m2 bar. Now m is equal to x1 m1 bar plus x2 m2 bar. Now we replace this. What we do here is we put x2 as 1 minus x1 and we replace this in the resulting equation, and therefore we get that the partial molar property of species 1 is nothing but the total property plus x2 into dm by dx1, and m2, that is partial molar property of 2, is equal to m minus x1 dm by dx1. Now if we have the total molar property, an expression for the total molar property in terms of x1 and x2, that is the mole fractions of 1 and 2, We can use this equation to find the partial molar property at each and every point. This is one application of Gibbs Duhem equation. That ends my lecture. Hope you have understood the subject matter. Please put your comments. Let me know, did you get anything from this lecture? That is, did you learn anything from this lecture? This is very important to me. Please like and subscribe my videos. They motivate me to make more lectures. Have a great day, guys. Bye.